You're probably aware that there are a lot of things that float. Some things are obvious, like the helium balloons, but others are a bit more troubling. How in the world does a ship keep from sinking? Take a cylinder that is suspended in some liquid. We know that the liquid is applying a force to all sides of the cylinder. The forces acting at each horizontal level cancel each other out. However, we had discussed the change in pressure with depth of a fluid, so it makes sense that the force pushing down on the cylinder is not equal to the force pushing up on the cylinder. The force acting at the top of the cylinder is equal to the pressure at that depth times the area. So we can say that the force 1 is equal to pressure 1 times the area. The force at the bottom of the cylinder is equal to the area at the bottom times the pressure at that depth. So force 2 acting on the bottom of the cylinder is the pressure 2 times the area. So how do we find the pressure at that depth? Well, we know that the top of the cylinder is submerged at a depth of h1, and the bottom of the cylinder is submerged at a depth of h2. We also know that the pressure increases as we go down further in our fluid, and we can find that by taking our depth times rho, g, and a. The differences in these two forces is known as the buoyant force. This buoyant force is the result of the net upward force caused by the pressure difference at depths in the fluid. If the buoyant force is greater than the weight of the object, then the buoyant force will push up on the object more and cause the object to float. If the weight of the object is greater than the buoyant force, then gravity will win and the object will sink. If the buoyant force and the weight of the object are equal, then the object will simply remain suspended at whatever depth it was placed. Another way to look at this is to look at the weight of the fluid that is displaced. When you put an object in fluid, it basically shoves the fluid out of the way. The amount of fluid displaced is equal to the volume of the object. If we take the object out, the space that was occupied is again filled by the fluid. The weight of this fluid is called WFL and is supported by the surrounding fluid. So another way to figure the buoyant force is to find the weight of the fluid that is displaced. This is known as Archimedes Principle. So calculate the buoyant force on 10,000 metric tons of solid steel completely submerged in water. Okay, so buoyant force is found by finding the weight of the water that is displaced, and we know weight is the mass times the acceleration due to gravity. We are given the density and the mass of the iron, so our first step would be to determine the volume of the iron. We simply do this by taking the mass divided by the density. Since the iron is completely submerged, the volume of the steel will also be the volume of water that is displaced. This is good because we know that the density of water is 1 times 10 to the third kilograms per cubic meter. We can multiply that by the volume of the water displaced to give us the mass of water that is displaced. Buoyant force is equal to the weight of the fluid displaced, so we can take the g times the mass of the water displaced to find the buoyant force of 1.3 times 10 to the 7th newtons. If we calculate the weight of the steel, we find it to be 1 times 10 to the 8th newtons. This is significantly more than the buoyant force of the water, so the steel will indeed stay submerged. Well, what if we took that same steel and made it into a boat? What is the maximum buoyant force that water could exert in the same steel if we could displace 1 times 10 to the 5th cubic meters of water? Here we are given the maximum volume that the boat can displace, so we need to find the mass of the water. The density of the water is still 1 times 10 to the third kilograms per meter cubed, so we multiply that times the volume of our displaced water. Buoyant force is the weight of the water displaced, so we can take our mass and multiply g to find buoyant force of 9.8 times 10 to the 8th newtons. So simply by changing this shape of our steel, we can significantly change the buoyant force acting on it. Compare that to our original buoyant force, and we see that we could actually load our ship with up to 9 times its own weight and still be able to float. Archimedes' principle applies whether the object is completely submerged or partially submerged in the fluid. Take a ship, for example. Obviously, the ship is not totally submerged underwater in either of those diagrams, but the one on the right sinks down a little bit more than the one on the left. The buoyant force acting on the ship is still equal to the weight of the water that is being displaced. So in this case, the challenge is to figure out how much of the ship is submerged, because the volume of water displaced is not equal to the entire volume of the ship. Now hopefully it is obvious that the density of the ship is more than the density of the water. However, it does not seem to be sinking. So we need to find out what the buoyant force acting on the ship is and what the weight of the ship is. Some of the ship is submerged, so if we find the volume of that portion, we can compare it. How the density of an object compares to the density of the fluid determines the extent to which it is submerged in the fluid. The ship on the left is unloaded, so it will have less density than the loaded ship on the right. As a result, the unloaded ship will float higher in the water than the loaded ship. We can compare the volume of the ship submerged to the total volume of the ship to determine how much it will actually sink. This means we can compare the volume of the fluid to the volume of the object, since the volume submerged is equal to the volume of the fluid that is displaced. Since the volume of the fluid that is displaced is equal to the volume of the object that is submerged, we can also use density to relate those two values. The ship is floating, so that must mean that its mass and the mass of the water that is displaced must be equal. So we can rearrange this as well to say that the fraction of the object submerged in a fluid is equal to the density of the object divided by the density of the fluid. This density relationship between the object and the fluid is known as specific gravity. A hydrometer is a tool that is filled with air but has a weight at the bottom. The height at which the hydrometer floats is determined by the density of the fluid it is floating in. The gradations on the tube are calibrated so that you can directly determine the specific gravity. In this example, the hydrometer is floating at about the 0.87 level, indicating that the specific gravity is 0.87. This just means the density of that object is 0.87 that of the fluid it is floating in. So if we're floating in water, the object would have a density of 0.87 compared to 1 of that of water. So suppose a 60-kilogram woman floats in fresh water with 97% of her volume submerged when her lungs are full of air. What is her average density? The woman is 97% submerged in the water, so her fraction submerged is 0.970. If we arrange our equation to solve for the density of our person, all we need to do then is multiply this fraction by the density of our fluid. Since this is fresh water, the density is 1 times 10 to the third kilograms per cubic meter. So the average density of our person is 970 kilograms per cubic meter. Since she is floating in the water, it does make sense that her density would be less than that of the water.